Where is it? Where is your talk?
It's on here.
One?
Yeah. Yeah.
This one?
Yeah.
So Bernard Zygelman from UNLV, and he will discuss excitation and quenching of hyperfine levels in atomic hydrogen.
Okay, thank you, Hossein, and the organizers for inviting me to this workshop here. So the title of my talk is The Excitation and Quenching of, and I should stress over here, I'm going to be talking basically quenching and excitation of hyperfine levels, more specifically ground state hyperfine levels of atomic hydrogen. So as the universe cooled, electrons and protons recombined to form neutral atomic hydrogen, along with some neutral helium and trace amounts of deuterium, lithium, and charged matter. The standard theory describes the onset of the so-called dark ages at redshifts around 200, in which amorphous clumps of hydrogen gas, whose atoms are in their ground state, begin to congregate and eventually collapse to spawn the first stars that once again illuminated the universe. The detailed story of exactly how these clumps of atomic gas eventually led to stars and complex structure in the universe is far from complete, but 21-centimeter cosmology, which we'll hear more about in tomorrow's sessions, promises the capability of astronomers to peer into those dark ages and even allow the possibility of creating tomographic maps of that era. In this talk, I would like to dwell on some of the fundamental atomic physics aspects that enables these advances. The ability to see atomic hydrogen in its ground state depends on a parameter called the spin temperature of atomic hydrogen. The latter is determined by both the collisional properties of hydrogen atoms and by their response to radiation. And it is these two aspects which will be the focus of my talk here. So one of the fundamental questions that is enabled in the last few years is this idea of making tomographic maps of atomic hydrogen in the dark ages and beyond. And overview of my talk is the history and survey of spin exchange, which is some of the fundamental collision data that determines the theory behind this 21 centimeter absorption. I'll also talk a little bit about spin exchange frequency shifts, and finally some brief words on the field Wuthausen scattering. It's been known for some time that the magnetic interaction between the electron and proton results in a small splitting of the ground state levels of hydrogen atom. These hyperfine levels, labeled by the total spin angular momentum quantum number F equals 0 for the lowest level and F equals 1 for the upper levels, in its ground state, the hydrogen atom can absorb or emit magnetic dipole radiation at 21 centimeters and induce transitions between these two levels. The 21 centimeter line has played an important role in the development of radio astronomy since being discovered almost 60 years ago, and it has played a central role in the development of the hydrogen maser. The ability to see either absorption or emission depends on a quantity called the spin temperature. An expression for it was first given by Purcell and Field. Here, the parameters y sub c, down here, are determined by the collisional properties of the gas, y alpha, by the response of hydrogen to Lyman alpha radiation, and TCMB is the background radiation, microwave background temperature, and T gas is the kinetic temperature of the gas, and T alpha over here is the Lyman alpha colored temperature. And so this fundamental equation, which was derived first by Field and Purcell, determines the spin temperature of your environment. Again, as I mentioned before, I'm primarily going to be talking in the region where Y alpha over here is 0. So basically, that's the dark age universe. In the dark ages, Lyman alpha radiation is not present, but collisions among hydrogen atoms, and to a lesser extent with residual electrons and ions, can drive the spin temperature away from the temperature of the microwave background. The latter is required for observation of absorption or emission features. Purcell first investigated the role of collisions in controlling the spin temperature, and initially, in his first paper in the early 50s, when the 21 centimeter line was discovered, the main collision mechanism that was generally known was, of course, the spin-spin interaction between two hydrogen atoms, since there's an open shell electron that has a magnetic moment, and it was thought that this part of the Hamiltonian causes the spin-flipping transitions. However, a few years later, a quote over here, talking with Victor Weisskopf, Norman Ramsey, and other investigators down at Princeton, they realized actually there is another effect, which is now called spin exchange, which is really much larger than this effect coming from the magnetic interactions. And so the first paper on this quantity, and it's important in determining the 21 centimeter line of collision, the role of collisions in the 21 centimeter line, was given in this landmark paper in 1956. So, what is spin exchange? During a collision, two approaching atoms will evolve along the Born-Oppenheimer potential curves that correlate to the asymptotic states of the hydrogen atoms. If the electronic spin approaches in the singlet state, they evolve on the ground singlet sigma g potential surface. Alternatively, if they approach as a triplet electronic spin state, they evolve along the triplet sigma mu curve. As the atom separates, interference between the acquired dynamic phase histories result in a spin exchange. Alternatively, we can think of spin exchange as being induced by an effective Hamiltonian that includes a Heisenberg scalar spin-spin operator whose coupling constant depends on the energy defect at a given internuclear separation between the two Born-Oppenheimer surfaces. So this over here is the previous magnetic interaction that I discussed, but this is the effective Hamiltonian that induces spin exchange transitions. And the important thing to realize is similar structure over here. There's a Heisenberg type of operator both here and here. There's also an anisotropic term. However, the important difference being is that the effective coupling constant depends on the splitting of the two Born-Oppenheimer surfaces for two ground state hydrogen atoms coming together, whereas in a magnetic interaction, of course, it has a long range but very weak coupling constant given by the fine structure constant squared. The collision theory for spin exchange has been worked out by several groups. The quantum mechanical theory was first developed by Delgarno in 1961, and so this year would be the 50th anniversary of that landmark paper, and generalized to include quantum symmetry effects by Smith and Allison Delgarno in the late 60s. The elastic approximation of Delgarno ignores the finite hyperfine energy defect and allows great simplification in the numerical effort required to calculate cross-sections. At very low temperatures on the order of the hyperfine splitting, one expects that the assumptions of the elastic approximation are no longer valid. For this reason, we developed a multi-channel collision theory that takes into account the finite hyperfine energy defect. This generalization comes at a cost. It requires calculations involving 16 channels, and the elegant simplicity of the elastic approximation is lost. At lower energies, one must itemize all possible level-dependent cross-sections when solving for the rate equations that determine the populations of the hyperfine levels. However, for gas temperatures of astrophysical interest, typically above 1 Kelvin, we only require an average of two distinct cross-sections, which we call sigma plus and sigma minus. The latter involve contributions coming from even and odd partial waves, respectively. An average over a Maxwellian distribution yields the collision rate coefficients K plus and K minus that are given by this expression up over here. Here we show the results of our recent multi-channel calculations of a few years ago. It confirms the validity of the elastic approximation, predicting rate coefficients that differ from the latter by only fractions of a percent. The major difference between the results presented here and those of Delgarno and Allison is due to the availability of higher quality potential energy surfaces. Primarily through the efforts of Wolniewicz and co-workers, as well as the work of Michael Jameson and Alex over the last few decades, has the quality of these potential surfaces given us such accuracy in our collision calculations. The features in these cross-sections represent shape resonances, these peaks over here. which play a significant part in determining the overall rate. Shape resonances are very sensitive to the details in the molecular potentials, and so high-quality molecular data is essential for accurate cross-section calculations. Here's an illustration of why we have these shape resonances. Basically, you have a shape resonance. If you look at the original Born-Oppenheimer state, which is given by the lower curve over here, the singlet sigma g curve, then if you look at two colliding atoms at a given particular relative angular momentum, that extra centrifugal barrier will provide more energy and basically will lift this potential surface up to this effective type of potential curve given over here. You see a small bump in that surface over here, which is magnified in this diagram. So if a collision system comes in with a certain energy which is below this threshold, there's a possibility for tunneling and getting trapped into these quasi-bound levels that can occur inside the hydrogen molecule. And so in this diagram, this is for the particular J equals 5 angular momentum state for the colliding H2 system. I've just drawn the wave function, what it looks like as you sort of ramp up the energy and you approach a resonance. You see a large increase in the amplitude, which means a quasi-bound state is formed. Likewise, there's a long delay time in here when you hit this resonance, and that causes these bumps or these spikes in the cross sections that you saw in the previous diagram. Again, these resonances can be quite important. For example, we found the J equals 5 resonance that I had on the previous slide contributes as much as 15% to the value of the spin temperature in the important region where Z is around 50, redshift is around 50. So again, over here, just looking at, this would be the contribution, the red line without the resonance, and this would be the contribution with the resonance. And this is the change in the effective rate coefficient, which again, when you put that into the rate equations for determining the spin temperature, gives a different spin temperature. At very low collision energies on the order of below 1K, multi-channel effects begin to manifest. Here we see the breakdown of the elastic approximation, which we also note that the cross-sections fragment into components corresponding to the various hyperfine states of the two-atom system. So luckily for us in regions of astrophysical interest, which is somewhere in this region, you see that the dashed line over here corresponds to the calculations given by the elastic approximation of Dalgarno. The full lines over here correspond to the multi-channel calculations, which are much more numerically intensive effort to produce them. But you see the excellent agreement in this regime, which is of interest in astrophysics. Of course, as you go down to lower energy, then major differences do arise between the elastic approximation and the full multi-channel results. Here we compile and compare the results of theory and experiment for hydrogen spin exchange cross-sections. So these are various theories and experiments over the years. The original calculation by Field in the 1956 is given the rate, well, the effective cross-section over here, the average cross-section is given by this dashed line. In 1961, these are the initial results by Dalgarno. Then later on, Allison, who was also in Dalgarno's group, produced these results over here, the solid line over here. These results are also in agreement and harmony with more recent calculations I did that I haven't shown on this particular diagram, which was shown on the previous slide. There are also new experimental results. There's some experimental results sort of in the room temperature range that were performed in the 1970s by this group up here. But more recently in the DAISY ring, the storage ring in Hamburg, Germany, low energy results, which are, again, are very important for astrophysical interest because these correspond to sort of temperatures you would have right around Z is equal to 50 or so. In that regime, these experiments were performed most recently in 2008 over here. And also, I've just also extended the calculations up into the higher collision energy range over here, given by this red line. So you see that there's fairly good consensus now between experiment and various theories over the years to what the spin exchange cross-sections are, at least in this particular region that is important for astrophysical applications. I do want to make a note, though, that is not the case at very low temperatures in the regime below into millikelvin. There's still some very serious discrepancies between the results of calculations and experiments measuring parameters that determine the physics, hydrogen mazing frequency shifts and things of that nature. So, in addition to inducing transitions among hyperfine levels of hydrogen atoms, spin exchange can also lead to frequency shifts of a resonance line in the hydrogen maser, that is the A to C transition. Measurements of this line in comparison with theoretical data provides yet another test for the quality of the potential curves used in our calculations. Here we give the result of the calculation for the shift parameter using the multi-channel theory. Comparison with experiment and the elastic approximation calculations of Allison show excellent agreement. So again, these are our multi-channel calculations we performed recently, but in order to compare experiment, you have to take so you see all kinds of oscillations, because you notice this cross-section is not a typical cross-section. It can either have a plus or minus, so it goes through a resonance. It goes from positive to negative values. And lots of oscillation, lots of detail in there. But then when you take a Maxwellian average over that cross-section, you get this solid red line over here. The crosses over here represent an earlier calculations using the elastic approximation by Allison. And there's one experimental data point taken from hydrogen maser data, and you see there's fairly good agreement. Again, at this temperature, there have been experiments in the 1990s by a UBC group, and also here a group at Harvard at low temperatures again. And unfortunately, in that regime, as I said before, there is some serious disagreement between the theoretical data and the experimental data. Though frequency shifts are important at low temperatures and higher density, we were led to speculate on the relevance of such shifts in astrophysical applications. So my question is, could we see these shifts all the time in hydrogen masers, also in Bose-Einstein condensates, but could you see them in astrophysical environments? This might be interesting because these shifts split these lines in a different manner. So there could be a splitting of this 21 centimeter radiation if this effect was important. Now, is that a possibility? Well, there are certain environments. Here's a picture of a simulation from a few years ago where you have the collapsing clouds of dense atomic hydrogen forming during the star formation phase, the first stars. And you see that from this diagram, you see that these simulations include densities of hydrogen that get quite large, up to on the order of 10 to the minus 19 hydrogen atoms per cubic centimeter. Also, the temperature range is, of course, higher too. Of course, these are very small regions over here, but would spin exchange frequency shift be important in these types of environments? So for that reason, I just calculated these frequency shift parameter curves that I showed you before in the lower temperature regime over here, where most experiments have been done, and extended them up to higher temperatures. That is relevant for the type of environments you have in these collapsing clouds. And you do actually get, I mean, you see that there's a zero over here, so this thing oscillates around zero. But when you average over this cross-section, you do get an effective rate at various temperatures that is small, but it's not insignificant. And so if you use the type of densities that you had in the previous slide that I showed, this would predict a splitting of the resonance line over here on the order of about 100 megahertz or so. Whether something like this can be observed or not, I would have to ask the experts who model these types of systems. So after realizing the significance of spin exchange and hydrogen atom collisions, Purcell and Field commented on the relevance of the direct long-range magnetic interaction that he later dismissed in that second paper. And actually, I'll put the quote over here. The estimate for that, he predicted that effect to be 0.01% of spin exchange. And he said the estimate could be refined, but there is no point in doing so, which seems reasonable. But I found this sufficient justification to proceed with the calculations. So over here, the solid lines represent recent multi-channel results where I calculated these magnetic spin flipping transitions in addition to the spin exchange. Again, as predicted, they're extremely small when you look at the cross sections. They are on order 10 to the minus 4 smaller. The spin exchange, but again, they could be important in these dense halo regions where you have higher densities of hydrogen gas. And also it's important in terms of selection rules because it allows certain spin flipping collisions that would change the polarization properties of the gas, which is not, you cannot get just from spin exchange. So there is reason for calculating these. One mild surprise in these calculations is that because the interaction is so weak, you might expect that the Born approximation would be valid to calculate this. And indeed, at low temperature, the dashed line over here, Born approximation results, the solid line are the full multi-channel results, and you see excellent agreement. And people have seen have used the Born approximation in BECs in very cold environments for these types of dipolar spin flipping transitions. But actually, in astrophysics, as you go up in energy, you see that predicts the Born approximation predicts a constant cross-section, whereas the full multi-channel results predict a cross-section that goes down. And we can understand this because if you look at the Hamiltonian for the dipolar interaction, it has a 1 over r cubed. And in the Born approximation, you just assume the system comes in as a plane waves and leaves as a plane waves. So that allows the two hydrogen atoms to come together, and that 1 over r cubed interaction dominates at higher energy and predicts a constant cross-section at higher energies. In reality, of course, the two hydrogen atoms are not allowed to come together on top of each other. They have a repulsive core that prevents them from doing that, and that's illustrated over here in the multi-channel calculations. And you don't have to work as hard using multi-channel calculations to get this effect. If you do a distorted wave Born, you would also see the same type of thing. Okay, so having talked about spin exchange or collisions, let me just say a few words about the field of Woodhausen scattering, which was originally pointed out in the early 50s by Woodhausen, then later elaborated on more detailed for astrophysical applications by Field in 1958. And the idea is this, is that suppose you have a hydrogen atom in its ground hyperfine state. If a Lyman alpha photon is available, then that Lyman alpha photon can excite either the P1/2 or the P3/2 level shown over here. Branching rules then also allow you for this photon, once it's been absorbed, to then decay down into the excited state. So at the end of the day, what you have is an effective spin changing transition or hyperfine level changing transitions through going up to these higher states over here. And the parameter that determines the efficiency of this effect is given by this y alpha, which involves the various parameters. This is the related to the probability for making a Lyman alpha transition, pi alpha. This is the energy defect of the ground state hyperfine level. This is the 2-1 transition, 2 and 1 being over here, the dipole transition, and this is the temperature, the color temperature of the Lyman alpha line. So I call this theory A. This is the original theory that if you go back to the paper of Field and also Meisken and other people based on this point of view. There's an alternative description, or maybe a more modern description, which, for example, a good example is given by the paper by Harada in 2006. And that looks at this scattering event as a Raman scattering of a Lyman alpha photon. And so basically you have a Lyman alpha photon coming in, exciting, absorbing a photon coherently, and then re-emitting the photon. There's also a stimulating photon I have on this diagram. And then coming back to a ground state, but to a different hyperfine level. And so this Raman scattering event is given by the Kramers-Heisenberg formula, somewhat generalized to include energy denominators of here. E sub c are the energy denominators of the excited levels that the system excites into, but they could be complex energies because these excited states have finite lifetimes. And so in order to calculate the efficiency of this, you have involved integrals of this form that involve transitions between the ground state, the 2p states, and these are various tensor operators, electric dipole tensor operators for the problem. So when you work out the angular momentum algebra, and in this example over here, I've ignored the hyperfine splitting just to simplify the analysis. Of course, you can include that and go through the same procedure, but I did that just to prove a point over here. If you work out these coefficients, these angular momentum coefficients, they break up into products that depend, of course, on the angular momentum, both the J angular momentum and the F angular momentum, the total hyperfine angular momentum in the system, times a quantity which involves a line strength like this, but also an energy denominator summed over all intermediate levels over here, itemized by the, and I used over here the JJ coupling scheme. So again, you could put in, you could use the hyperfine scheme, but again, just to make it simple, I used the LS coupling and used the J quantum numbers to do the sum over the intermediate states. So suppose all these states, when you sum over all the possible J prime, and you have two J's, you have the J equals 1/2 and you have the J equals 3/2 for the 2p states. If you can ignore that energy defects, then all you have to do is look at the selection rules for these angular momentum 3J symbols and realize right away that this sum vanishes. So the important point over here is that it's actually the spin orbit operator which causes the splitting of the 2p levels, the 2p 1/2 and 2p 3/2, that actually gives you a non-vanishing Raman scattering cross-section over here. So if the spin-orbit interaction is ignored over here, then you would actually get that this effect will give you a null result for the Field-Wüthausen scattering. Or if you include it, another way of saying the same thing, if you include this effect now and you work out the sum over all the 2p levels over here, again, you could see that this, when you add up all these fractions over here, the total effect is going to be proportional to the energy defect, which is the same thing as saying it's going to be proportional to the spin-orbit interaction or the fine structure constant. In other words, it's saying the effect is small because that energy defect is small, or the spin-orbit coupling is small compared to all the other couplings. Now, in a paper in 2008, Dijkstra and Loeb called this effect quantum interference, and they showed by incorporating this, you take the expression that Field wrote down for y sub alpha, the efficiency for Lyman alpha coupling of the two hyperfine levels, is just modified by an additional Q term over here, which is basically an average of the photon flux over the line profile, including these quantum interference effects. And this has important implications, not if you're directly on the Lyman alpha, on resonance, but if you're slightly off resonance. So actually, rather than comment on this, I just like to pose a question to the audience. I mean, it seems that we have two ways of thinking about field-Woothausen scattering. In part A, it's seen basically as an incoherent process. In other words, that the way radiation is absorbed and then re-emitted are described by rate equations, where in the second point, you have no rate equations except for the n equals 2, just the two lower hyperfine levels, and the system, this scattering occurs as a coherent process. And they have very different predictions when you're going off resonance or when you're in the wing of the profile. So I'm not sure which of these is the correct way of thinking about field-Woothausen's scattering, but basically I'll just leave that as a question. So my summary is I've given a sort of survey of spin exchange data for the 21 centimeter cosmology applications. It seems that we're, in terms of looking at the accuracy of these cross-sections, the fidelity of these cross-sections, we're in pretty good shape. It seems that various theories and experiments seem to converge to a common value that is used in the modeling of the 21 centimeter absorption. I talked a little bit about spin exchange frequency shifts, and again posed the question, could this effect be important in very dense collapsing objects of hydrogen gas? And then finally, I sort of left the question open here about when we talk about field-Woothausen scattering, how should we think about this? So I'd like to thank the audience and be available for any questions.
Thank you. Questions for Bernard? What about with respect to multi-channel non-adiabatic environments?
So the question was, with the multi-channel calculations, what effect do non-adiabatic effects, which I didn't talk about here, would have? And the answer is we know that it would have considerable effects at very low energies, sort of in the region milli-Kelvin type of energies. And one way we understand that is that actually when you look at your system and you change the reduced mass for your system, so which is a very small effect. When you work, we're working this Born-Oppenheimer picture. In the Born-Oppenheimer picture, you take a very specific Jacobi coordinate system that involves the center of the nuclei of the two hydrogen, use the reduced mass for the nuclei of the two hydrogen. But then asymptotically, the system doesn't separate into just the two nuclei and two electrons. It separates as an atom as a whole. So if you use a reduced mass for the two hydrogen atoms instead of for the two nuclei, which again is a difference on the order of 1 in 10 to the 4 or so, you actually get a very big change in the cross-section on the order of 20%, which seems unusual. But one of the reasons why you have that is because we've neglected what are called the non-adiabatic couplings, which basically couple to higher excited states. And so if we had that in there, probably you would, first of all, you wouldn't see that discrepancy anymore, and it would be a more rigorous type of treatment, give you more accurate answers. But again, that will be applicable at very low energies on the order of milli-Kelvin regime. But I don't think it will be important in astrophysical environments, at least not in the type of systems that I talked about here.